All right, strap in, everyone, because today we're tackling something that might sound a little intimidating at first, but I promise it's way cooler than the name suggests.
Oh, yeah. Definitely agree with you there.
We are diving deep into the world of fluid mechanics, specifically Chapter 5 of Munson's Fundamentals of Fluid Mechanics, which, for anyone who's ever dipped their toes into understanding how liquids and gases move, this is like the go-to book.
Yeah, it's the Bible.
And today, we're going to try to make sense of finite control volume analysis, but in a way that even if you've never heard those words before, you'll walk away feeling like, okay, I actually kind of get what that means.
Yeah, how it's used, yeah.
Exactly, yeah.
And what I think is so cool about this approach is that it lets you look at the big picture of how fluids behave without getting bogged down in all the tiny little details.
Yeah, I mean, trying to track every single water molecule in a pipe, forget about it.
Yeah, that's a recipe for disaster.
Total chaos.
Yeah.
So instead, we're going to do define a zone, this finite control volume we keep talking about, and analyze what's going on inside and at the edges of that zone.
Right, exactly.
Is that kind of like, I don't know, studying the flow of people in and out of a stadium during a game?
Yeah, exactly like that. That's a really good analogy.
Okay, good. I'm glad that works. So then Chapter 5 goes even further and uses average values for stuff like velocity and density within that control volume.
Yeah.
So it's kind of like summarizing a giant report. You get the main points without every single number and statistic.
Precisely.
I'm already seeing how this could be super useful. So what's the first big concept we run into using this zoomed out method?
Well, the first thing you gotta understand is the principle of conservation of mass. It's captured by this thing called the continuity equation. Think of it like your budget.
Oh, okay.
What comes into your account has to equal what goes out, otherwise your balance changes, right?
All right, of course.
With fluids, the currency is mass.
So if more fluid is flowing into our control volume than out, something inside has to be changing, like maybe the fluid is getting compressed.
Bingo. Equation 5.3 in the book spells this out in mathematical terms, but the idea is super straightforward. It's like matter can't just magically appear or disappear. It just moves around or changes form.
Okay, got it. Now I see that example 5.1 talks about ventilating a tank, which sounds pretty practical. What's the key takeaway there?
That one shows how assuming steady flow where things aren't changing like crazy all the time makes the math a whole lot simpler. Like, imagine you're designing a ventilation system. You need to know how much air you need to move to keep the environment safe, and the continuity equation is what gives you the tools to figure that out.
Makes sense. But what about situations where the fluid's density is changing, like air getting squished or expanding? Surely that complicates things a lot, right?
You'd think so, but actually no. The continuity equation still holds up. Example 5.2 goes through calculating airflow in a pipe where the density changes. And what's wild is that even though the mass flow rate stays the same, the velocity can change a ton.
Wait, so if a pipe gets narrower, the air speeds up to keep the same mass flow rate going, like when you squeeze a hose to make the water shoot further?
You got it. That's the power of this equation, even though it seems simple. It shows you these hidden relationships between velocity, density, and flow rate.
Mind officially blown. Okay, so far we've been picturing our control volume just sitting still. But what if it's moving? Like trying to analyze the jet engine on a plane that's in flight.
Ah, yeah, Chapter 5 covers that too. It brings in this modified continuity equation, equation 5.16. This one takes into account those moving control volumes. Think about a firefighter aiming a hose at something that's moving. The water's speed relative to the nozzle and the target's movement, both of those matter.
I can see how that gets really complicated fast. So by taking into account the movement of our control volume, it opens up a whole bunch of new scenarios we can analyze.
Exactly. It's like you add another layer of understanding to how fluids work. Even something as simple as a lawn sprinkler becomes super interesting when you start thinking about the moving control volume.
All right, I'm following so far. We've covered conservation of mass, but I know there's another big one in physics Newton's second law. How does that play into all this fluid stuff?
It all comes down to momentum. Just like a moving object has momentum, so does a fluid that's flowing. Equation 5.22, they call it the linear momentum equation. This one tells us that any change in the fluid's momentum has to be caused by forces acting on it.
Okay, I'm looking at figure 5.2 here, and it looks like our control volume is being pushed and pulled from every direction. So it's not just about how fast the fluid is moving, but also which direction it's going.
Exactly. Even a tiny change in the direction of flow can have a massive impact on the forces involved. Example 5.10, where they have a water jet hitting a vein, this shows it perfectly.
Okay, I'm picturing a powerful jet of water slamming into a stationary object. What's the takeaway there?
The force you need to hold that vein in place depends a lot on how the vein redirects the water flow. If the vein just deflects the water straight back, you need a much stronger force than if it diverts the water at a 90-degree angle.
Wait, really? That's not what I would have guessed. I thought a 90-degree turn would need more force. So even small changes in flow direction can make a huge difference in the forces.
Absolutely. And that's exactly why understanding this linear momentum equation is crucial for designing all sorts of things, from pipelines to dams.
This is amazing. We've gone from the continuity equation to the linear momentum equation. Now, I'm ready for the next fundamental principle, which I'm guessing is the energy equation, right? Bring it on.
You got it. First law of thermodynamics tells us that energy can't just be created or destroyed, only transformed. And guess what? This applies to fluids just the same.
So just like with mass, the total energy inside our control volume has to stay the same unless energy is added or taken away from the system.
Exactly. But the energy equation in fluid mechanics gets a bit more complicated because we have to think about all these different forms of energy: internal energy, kinetic energy, potential energy, and even the work that's done by pressure forces.
Okay, so a fluid can have energy stored within it, energy from its motion, energy based on its height, and energy from pressure.
Exactly. And equation 5.64 ties all these forms of energy together really beautifully. It basically says that the total energy going into our control volume plus whatever energy is added to the system has to equal the total energy leaving plus any energy that gets lost.
I see where you're going with this. Another example. What kind of real-world problem can the energy equation help us solve?
Think about pumping water uphill. Example 5.20 shows how we can use this equation to calculate the power the pump needs, taking into account all those different forms of energy.
So the energy equation basically helps us figure out how much work a pump has to do to fight against gravity and friction. That's incredibly practical.
It is. And it also highlights a big challenge in fluid mechanics, which is figuring out how to minimize those energy losses due to friction.
Friction. The bane of every engineer's existence. I bet that's where things start to get even more interesting, right?
Yeah, I bet. And to really get a grip on how friction messes with fluid systems, we need to dig into this really cool thing called non-uniform velocity profiles.
Well, you're telling me the fluid doesn't always move at the same speed everywhere in a pipe?
You got it. And that difference in speed can have a huge impact on how much energy gets lost. But we'll save that juicy tidbit for after the break. Stay tuned.
Okay, now I'm really on the edge of my seat. We've covered so much already, from the continuity equation to the linear momentum equation, and now the energy equation. And I can't wait to unpack this whole non-uniform velocity profile thing.
Yeah, it's really interesting stuff.
I'm sure it is. All right, we'll be back in a flash to continue this fascinating journey through the world of fluid mechanics.
We'll be right back.
Okay, so before we went to break, we were just starting to get into this whole idea of non-uniform velocity profiles. It sounds like we can't just assume that all the fluid in a pipe is moving at the same speed, which kind of blows my mind. Help me wrap my head around this.
Okay, imagine a highway, right? You've got a speed limit, but some cars are zooming along in the fast lane,
Yeah.
while others are stuck behind a slow truck. It's the same idea with fluids in a pipe.
Okay, so the fluid closer to the walls of the pipe is going to experience more friction, like those cars, in traffic,
Right.
and move slower. Got it. But why does this matter so much for energy loss?
Well, because friction creates heat, right?
Yeah.
And that heat is basically energy that's just lost to the system.
Mhm.
So the bigger the difference in speed within the flow, the more non-uniform the velocity profile is, the more friction you're going to have and the more energy you lose.
So it's kind of like those speed demons in the fast lane are creating turbulence and chaos.
Yeah.
Making the whole system less efficient.
Exactly. And to capture this effect, engineers use this handy tool called the kinetic energy coefficient. Oh, yeah.
It's denoted by the Greek letter alpha.
Right, alpha. We mentioned that earlier. It basically tells us how much the actual kinetic energy of the flow differs from what we'd calculate if we just assumed everything was moving at the average speed. Like, that would be way too easy.
Way too
Okay.
easy, exactly. Equation 5.86 in Munson's book, that's the one that defines alpha. It's the ratio of the actual kinetic energy to the kinetic energy that you'd get if you just use the average velocity. So a higher alpha means a more non-uniform velocity profile, and you guessed it, more energy loss.
Got it, got it. So alpha is like a measure of how chaotic the flow is, with higher values meaning more turbulence and wasted energy. Is there a way to visualize this to make it more concrete?
Sure. Imagine two pipes, they have the same average flow rate, okay?
Uh,
One pipe, the velocity profile is perfectly uniform, everything's moving at the same speed. In the other pipe, you've got a very non-uniform profile, with some parts moving way faster than others. Guess which one's going to have more energy
the
loss?
one with the uneven flow, right? You got it. That one's going to have a higher alpha and experience way more energy loss because of all that internal friction.
That makes sense. It's like comparing a well-organized marathon where everyone's running at a steady pace to like a chaotic stampede where people are bumping into each other and wasting energy.
That's a great analogy. And what's really fascinating is that alpha is always greater than or equal to 1. It's only equal to 1 in those ideal situations
Hmm.
where you have perfectly uniform flow, which, let's be real, almost never happens in the real world.
So in most cases, if we really want to understand energy losses, we got to factor in alpha. And the book gives us formulas for calculating alpha for different types of flow, right?
It does. Example 5.27 is a really good one. It looks at flow through a pipe with a parabolic velocity profile, which is what you typically see with laminar flow, that nice, smooth, orderly kind of flow.
Right, laminar flow. That's where the fluid moves in parallel layers, like sheets of paper sliding over each other. So even in that type of flow, which seems pretty well behaved, we still have a non-uniform velocity profile and an alpha that's greater than 1.
Exactly. In that example, the kinetic energy coefficient turns out to be 2, meaning the actual kinetic energy is double what you'd calculate if you just assumed a uniform velocity profile.
Wow, that's a huge difference. It really makes you realize that you can't just ignore those velocity variations if you want to get an accurate picture of energy losses.
You got it. And these principles apply to all kinds of fluid systems. We're talking pipelines, pumps, turbines, even the airflow over an airplane wing.
This is incredible. It seems like we've covered so much ground already in these first few sections of Chapter 5. What other amazing concepts are waiting for us in this world of finite control volume analysis?
Well, we've covered conservation of mass and momentum, and we've dug into the energy equation. But there's one more fundamental principle that governs how fluids behave, one that has a lot to say about how efficient processes are and whether they can be reversed or not.
Okay, I'm intrigued. Give me more.
We're talking about the second law of thermodynamics and the concept of entropy.
Ooh, entropy. I've always found that to be a bit of a mysterious concept. People describe it as a measure of disorder or randomness, but I'm not quite sure how that applies to fluid mechanics. Can you break it down for me?
Absolutely. When it comes to how fluids flow, entropy is all about processes that can't be perfectly reversed. It's like a one-way street. Once some things happen, you can't go back and undo them completely.
Like that classic example of spilling a glass of milk.
Yeah.
You can't really put all those tiny droplets back together perfectly.
Exactly. That's a great analogy. And in fluid mechanics, a prime example of this kind of irreversible process is friction.
Ah, friction, our old friend. So anytime we have friction in a fluid system, we're increasing entropy. It's like the energy is becoming less organized, more spread out.
You got it. Think about a deck of cards. If it's all nicely ordered, that's low entropy. But when you shuffle it, you increase the disorder, the entropy. Same thing with fluids. When friction acts on a fluid, it disrupts that nice, orderly flow and increases entropy.
Okay, so the more friction we have, the more entropy increases, and the more energy we basically lose to this less organized state. Is there a way to actually quantify this relationship between entropy and fluid flow?
Absolutely. Munson's got us covered there too. Equation 597, it's called the entropy balance for a control volume. This one describes it mathematically. It tells us that the rate of change of entropy within our control volume plus the net flow of entropy across the boundaries has to be greater than or equal to the amount of entropy transferred due to heat.
All right, I'm trying to wrap my brain around this equation. What's so important about that greater than or equal to part? What's that telling us about entropy and how fluids flow?
That's where the idea of irreversibility comes in.
Hmm.
If you had a process that was perfectly reversible, meaning no friction or any other losses, the equation would just be a simple equality. But in the real world, friction always exists, at least to some degree.
Real well.
So that means the rate of change of entropy is always greater than the entropy transferred due to heat.
So that inequality is basically a warning sign, telling us that some energy is being lost to these irreversible processes, those one-way streets that we can't go back on.
Exactly. It's like a fundamental limitation set by the second law of thermodynamics. And it highlights how deeply entropy is tied to the arrow of time in fluid mechanics. Those energy losses from friction mean we can't just rewind the clock and perfectly recreate the initial state of the system.
Wow, that is profound. It's amazing how these ideas that seem so abstract actually have such concrete implications for how fluids behave. Makes me think about the efficiency of engines and other systems. The more entropy we generate, the less efficient they become.
You got it. Understanding entropy is key for designing systems that are efficient and sustainable. It helps us see those built-in limitations and figure out how to minimize those irreversible losses.
This is mind-blowing stuff. We've gone from picturing control volumes to tackling this concept of entropy. It's incredible how much depth and complexity there is to something as seemingly simple as a fluid flowing.
It is pretty amazing, and we've only just started to scratch the surface of what Chapter 5 has to offer. There's a whole lot more to explore.
So we've come a long way, haven't we? We've explored conservation laws, wrestled with the idea of momentum, and even dipped our toes into the deep waters of entropy. I feel like I've gained a whole new appreciation for how fluids behave.
And we've barely scratched the surface of what finite control volume analysis can do. Chapter 5 still has some treasures waiting for us.
We'll lead the way. I'm ready for more.
You know, we've talked a lot about how to use these principles to solve specific problems, but I think there's something bigger here. Fluid mechanics isn't just about crunching numbers and solving equations. It's about understanding these fundamental forces that shape the world around us.
Yeah, that's a good point. It's easy to get so caught up in the details of control volumes and equations that we forget to step back and see the bigger picture.
Yeah.
So how does all of this connect to that bigger picture?
Think about it. Fluid mechanics helps us understand and predict so many things, like the weather patterns that drive our climate, the flow of blood through our veins and arteries, the design of airplanes and rockets.
Wow, it really is everywhere, isn't it? From the tiniest capillaries in our bodies to these vast ocean currents.
Exactly. And the amazing thing is that those same basic principles we've been talking about, conservation of mass, momentum, and energy, apply to all these different systems.
It's pretty incredible, right? These underlying laws that govern everything around us. It's like having a master key that unlocks the secrets of the universe.
Exactly. And what's even more exciting is that we're always pushing the boundaries, finding new ways to analyze even more complex fluid flows, like computational fluid dynamics. That's revolutionizing how we design everything from cars to wind turbines.
So even though we've learned a lot today, there's still a whole universe of knowledge out there waiting to be discovered in the field of fluid mechanics.
Oh, absolutely. And the coolest thing is that it's all around us. Every time you turn on a faucet or watch the wind blow or see a plane take off, you're watching fluid mechanics in action.
I'll never look at a flowing river or a swirling cloud the same way again. This deep dive has really opened my eyes to just how complex fluid behavior really is.
And it all starts with those fundamental principles we talked about. Mass can't be created or destroyed. Forces cause changes in momentum. Energy is conserved but can change forms.
Those are the ideas that underpin everything we've been discussing today. And by using them, we can analyze and solve all sorts of problems related to fluid flow.
Exactly. Whether you're designing a new irrigation system, making a race car more aerodynamic, or even just trying to understand how a hurricane forms, fluid mechanics gives you the tools and knowledge you need.
It's been an incredible journey. We started by defining a simple control volume and ended up exploring the complexities of entropy and the second law of thermodynamics.
And I hope you've come away with a new appreciation for just how amazing and important fluid mechanics is.
I definitely have. It's been an honor to explore this fascinating subject with you.
The pleasure was all mine. Now go out there and see the world with fresh eyes, noticing the intricate dance of fluids everywhere you look.
I will. And to all our listeners, thank you so much for joining us on this deep dive into the fundamentals of fluid mechanics. We hope you've enjoyed the journey and learned some valuable insights along the way. Until next time, keep exploring, keep learning, and most importantly, keep those curious questions coming.